Hey again, guys. Thanks for, again, coming back. You guys are crazy. Another video. PV equals nRT. Ideal gas equation describes pretty completely how most gases behave in normal conditions. Oh yeah, oh yeah, oh yeah. So here we go. I snipped this from my lecture notes because I was so proud of it and I didn't want to write it again. But it's good to think about. P is for pressure in atmospheres, V is for volume in liters, N is for number of moles of gas, R is the ideal gas constant, and T is the Kelvin temperature. So because gases can change their temperature, we can have different amounts of gas and particles, different volumes, different pressures. This kind of ties it all together. The gas constant is nice because it reminds me that if I want to use this equation to be sure it's going to work, I should probably use liters, atmospheres for pressure, liters for volume, moles for number of particles, Kelvin for temperature, definitely Kelvin for temperature. Also, because gases are so fickle and variable, we like to refer to standard conditions. For a gas, standard temperature is 0 Celsius, which is 273.15 Kelvin, and the standard pressure is 1 atmosphere pressure. Did this little calculation. If I had 1 mole of gas, doesn't really matter what gas it is, interestingly. Could be any kind of gas. Methane, helium, sulfur hexafluoride, uranium hexafluoride, doesn't matter. 1 atmosphere pressure, gas constant, Kelvin temperature, the volume comes out to 22.4 liters. This is called the standard molar volume. If you warm things up a little bit, because who really wants to work in a 0 degree Celsius laboratory, changes temperature to, say, 298 Kelvin or something like that, and this bumps up to about 24 liters or something like that. Other manipulations or rearrangements of that equation, if I have a gas undergoing change or in 2 different situations, I can compare situation 1 to situation 2 with a little ratio like this. PV equals nRT. Situation 1, situation 2. But of course the R's cancel like that, and I have P1 over V1, or P1 V1 over P2 V2 equals N1 T1 over N2 T2. Or you can also rearrange like this. You could take this down to the bottom here and this up the top here, and you realize that this ratio would be equal to the gas constant, and or you can eliminate that gas constant and write it like this. Hate to burden you with too much to memorize, but you know PV equals nRT, and maybe you can rearrange it algebraically to suit your specific needs. Here's a simple example of straight up using the equation. Methane gas, 3.1 atmospheres, temperature is 300 Kelvin, volume is 4 liters. Since we're given all this info in a straight up fashion, liters and Kelvin and atmospheres, I can just plug it right into the equation and solve for N, the number of moles of methane. Pressure, volume, gas constant, Kelvin temperature. But do you realize you can solve for any one of these unknowns? So if pressure was unknown, if volume was unknown, in this one my number of particles are unknown, or temperature were unknown, the gas constant is always known, given to you. You can solve for any one of the unknowns. This one comes out to about half a mole of methane, and voila, because you know how to change moles to grams, it's super convenient. This is one of the first ways that chemists, scientists had of actually counting number of particles by weighing in a gas, especially in a gas, because gases are so buoyant you can't really weigh them. But if you knew a certain volume, pressure, temperature, gas constant, you can solve for moles and solve for mass of the gas. Let's see. What if we wanted to change conditions of a gas to standard temperature pressure conditions, which is often done? I collect a gas at 28.7 degrees Celsius. The volume is 275 milliliters, and the pressure was measured at 683 millimeters of mercury, also known as 683 torr. What is the volume of this gas at standard temperature pressure? Well, I might use this one, but I realize the number of particles isn't changing and the gas constant isn't changing, so I can cross those out. I will need to use Kelvin temperature, so I add 273.15, and my standard temperature is just 0 Celsius, which is 273.15. When you're in doubt as to whether or not you really need to change pressure and volume and number of particles to moles, pressure to atmospheres, volume to liters, In some of the individual gas laws, you may not need to do that, but it's not a bad idea if you're in doubt. Sometimes if you do it to both sides of the equation, it ends up canceling. It doesn't matter. But for us right now, let me do it. 683 millimeters of mercury multiplied by a conversion factor. 1 atmosphere is exactly 760.0. I think that's an exact number. Anyway, 3 sig figs here, divide 3 sig figs here. And my volume, 275 milliliters, 0.275 liters. So now I'm getting ready to put it in the equation that I had from above. Here's my collected gas conditions. Here's the Kelvin temperature, T1, the volume, V1, the pressure, P1, standard pressure, unknown volume at standard conditions, standard temperature, and just sulfur V2. Let's see, does that make sense? I started at 275 milliliters, and because I made it colder, most gases shrink when you make them colder, and the pressure is also, the pressure is building from 0.89 at almost 0.9 atmospheres to 1 atmosphere. So this factor and the temperature factor would both bring this volume down from 275 milliliters to 224 milliliters. Here's a cute question. How many molecules are in your average breath? Assume your lungs can hold 2.5 liters-ish. The pressure in Salt Lake City, 740 torr, and the temperature of your body, 37 Celsius. We need some corrections. Let's change the torr to atmospheres. That's a common thing. You should memorize 760. You got to be able to just divide the torr or millimeter of mercury by 760 to get atmospheres. Add 273.15 to get the Kelvin temperature. And now we're ready to plug them in there. So the pressure, the volume, the gas constant, Kelvin temperature, I'll fit in there to find N. And in a way, N is the most common thing we're trying to solve for in laboratory practicality kind of a sense, because, is that a word? Practicality? I don't know. Because we want to know how much gas we have in a particular experiment we're using, and PV and T kind of describe that. Anyways, that comes out to 0.0975-ish. Sometimes I subscript the last number to say it's not significant, but I'm not going to round till the very end. And that moles converts to molecules of air. And I think it's about 58.7 million trillion air molecules. That's just unbelievable how small those particles are. And how fast they're moving. We'll learn that later. One last example, collecting a gas over water. Very, very, very famous experiment where I have, maybe I have a gas tank over here and I just let some gas out of the gas tank. Or in the olden days when they didn't have gas tanks, you took a chemical compound and heated it up. And you bubbled that gas that came off through some water. This is like an upside down beaker of water. And when you're done collecting the gas, the level of the water outside should be equal to the level of the water inside. If they weren't exactly equal in height, this jar might need to be raised or lowered so that we have some knowledge of the pressure inside this container being equal to the pressure of the air outside the container. Well, here's some things we need to measure. And indeed, that's the pressure, air pressure. So if I know I have 30 inches of mercury, and if I imagine I just look this up on KSL.com, or the weather dude delivers in the good old US of A the air pressure in inches of mercury, I might need to change that to millimeters of mercury. I should know the gas and water temperature. How cold or warm is this water? Because as it turns out, warmer water would allow more water to get up in, water vapor to get up in this airspace. So we're going to have to take that into account in just a second. The mass reduction in the generation tube. So if I measure this, weigh this thing before I heat it, then I heat it and the gas bubbles away, and I weigh it again, its mass decreases. Sure, I must let it cool off before I weigh it again, but it loses almost a gram in that heating. And the volume of gas collected, let's say exactly half a liter. Adjustments. I need to change the Celsius temperature to Kelvin and assume the water temperature is the same as the gas temperature. A pretty good assumption. The pressure was reported in inches of mercury. I got to change that to millimeters of mercury. 25.4 millimeters in an inch. So that just multiplies straight away. But I'm going to call that wet. And you know why I call that wet is because it's collected over water. And as the gas bubbles up through the water, it will collect some of that water vapor. And that water vapor will add to the total pressure. So this total 762 is too large. It includes some vapor pressure due to water. I just thought I'd clip this interesting little graph, kilopascals and degrees Celsius at, what are we at? 25 Celsius. At 25 Celsius right here, I can't read the graph too well. So I'll look up a big chart, and that looks like, can I zoom in that well? How's the, oh, there it is. It's right there. 25 Celsius, water vapor pressure. So as the water bubbles, as the gas bubbles up through the water, 23.756 millimeters of mercury of water vapor pressure come up along with it. So in my gas sample, this must be subtracted from my total pressure. That's a weird idea, but get used to it because it's common. It's a famous experiment done for many, many years. And so my millimeters of mercury, let's subtract the water vapor pressure here to get 738-ish. Non-significant. I'm just carrying them so I don't round too soon. Divide by 760 again, change to atmospheres. So finally we're ready to snug that into my PV equals nRT equation. All that stuff I'd worked hard to get. The pressure, the volume was easy. The gas constant, no biggie. I just added 273 to the 25 Celsius. This was the hardest thing to adjust, the pressure, to see that we actually knew what the pressure of the gas sample inside that jar, and that upside down jar over the water was. And lo and behold, small number of moles, 19.84 millimoles. Oh yeah, have you guys heard of millimoles? Oh well, 0.01984-ish moles of gas. But one last thing, the reason why this experiment is nice and famous is that I can take my mass of gas and divide it by the moles. That's really what molar mass is, just a comparison of the grams to the moles. So if you knew the grams and you knew the moles, you do the math and you find the molar mass of this gas, 46.4 grams per mole, or 46.4 AMU for one molecule. That's a crazy idea. If later we had discovered the formula for that gas, perhaps in a different experiment or by asking someone else that knew, C3H8, that adds up to 12, 12, 12 plus 8 is about 44. But if I carry more sig figs and I say, well, I came pretty close, this number is pretty close to this number, what's my percent error, by the way? It's an experimental thing, but interesting to do. Take what you got minus what you should have got compared to what you should have got. That gives you a decimal. Change to a percent. 5%, not too bad. Could be better, not too bad. Hey, thanks for watching, guys. See you in class. Good luck with this ideal gas thing. It can be tricky sometimes.